So this is the last video that I intend to make regarding bonding, the bonding unit. And then on Monday, I intend to do one other new concept to introduce you, and then we'll wrap it up next week. I'd like for all homework to be in by Wednesday, but I'll send a note on that. So on the website, this is today's May 14th of the homework page on the website. I've made a couple of videos already today. The first one is, I actually made this one first, but then went back and made this one for how to determine shapes of molecules, and then instructions for determining whether molecules are polar or not. And right now I'm making this one that I have labeled as pending. For those of you who want more detail after I do I'm going to make an attempt to kind of summarize this in kind of a short video. There's more on Khan Academy. And if you go to Khan Academy, you should look at this London dispersion force video, but then the first four of these, or at least the first three, you should take a look at. And the fourth thing I thought you might be interested in. But that's about 40 minutes worth of video watching about chemistry. So you can, but it's out there if you'd like to research it. Okay, so what I'm going to do is make the video that fits right here about attractions between molecules. So here I have two molecules, and I've tried to set them up so that they look like they're non-polar molecules. So they'd have electrons all around everywhere, just kind of spread out. But if I move them together, then what's going to happen is these electrons are going to repel those electrons, and the molecules are going to kind of distort, become a little bit lopsided, perhaps like that. And the same thing here. They become a little unevenly distributed so that this end becomes negative and that end becomes positive. And then some other molecule that was down here that was maybe non-polar, like that one, well, it sees this positive thing, and there's electrons over here, and they move over and they get attracted to it, and that causes it to distort so that it gets bigger over here and smaller over there, but then it doesn't stay there very long. So what happens is the electrons snap out of position, then back into position, then out of position, and back into position. And that makes for temporary polarity. This is only temporary. And while they're polar, they might attract other molecules, but the attractions are short-lived because the molecules can't maintain their polarity. So things around you like that are nitrogen and oxygen. Things that are non-polar have weak attractions between the molecules, which makes them more likely to be gases. And it's good that nitrogen and oxygen are gases because we breathe them all the time. Particularly oxygen is kind of important that it's a gas. All right, so that's one scenario. We call those London dispersion forces. You'll commonly see them abbreviated as LDFs. So LDF means London dispersion forces. All right, now I'm going to move off my creative way to move these together and just move into a more traditional approach. So now another option, remember those are two non-polars. So those are between non-polar molecules, or at least it's more, that's the only force that holds non-polar molecules to each other. I guess it's important that I point out that all molecules have these kind of sloshing electrons, if you will, sloshing, S-L-O-S-H. But for non-polar molecules, that's all that holds them together. If you have a polar molecule, you have these, but you also have another kind of attraction. So here's a picture of my attempt at a picture of a polar molecule. And this is a molecule that is always in that kind of a position. An example might be fluorine bonded to hydrogen, where you have that, or carbon bonded to oxygen. Notice I put the negative end down on the fluorine end because it's more electronegative. Or if you had carbon bonded to oxygen. So like that. So the electron cloud would be unevenly dispersed around the oxygen because the oxygen is more electronegative. So that'd make this end of the molecule negative, that end positive, and that's negative, and that's positive. So it's kind of easy to see why these molecules would act like little magnets, because they've got a positive pole and a negative pole, just like a magnet has a north and a south. So not only are they going to be held together by these LDFs, but they're also going to be attracted to each other because they have polarity, like magnets would be attracted to each other. So we call these dipole-dipole forces. And dipole-dipole forces are attractions between two polar molecules. So if you go back and look at the Khan Academy list, you'll see that his first little video is about London dispersion forces, and then he talks about dipole-dipole forces. And then the third video that he makes is a little video about hydrogen bonding. And hydrogen bonding is probably the most important kind of attraction between molecules. It's very, very important in biology, which is your course next year. It's what holds the rungs of the DNA ladder together. It's involved in multiple aspects of biochemistry. It's just a really important type of intermolecular attraction because it's strong enough to hold things together, but it's weak enough that you can break it easily. So hydrogen bonding happens when hydrogen is bonded to a really, really high electronegative element like oxygen. Oh, did you notice that's water? So if I have water molecules sitting next to each other, there's a positive and negative attraction. This end of the water molecule is positive, this end's negative, and they attract each other. So the hydrogen bond is the attraction between the molecules. Hydrogen bonding can only occur when you have hydrogen bonded in a molecule to three elements. So if you have hydrogen bonded to oxygen, hydrogen bonded to nitrogen, or hydrogen bonded to fluorine, those three types of bonds set up hydrogen bonding between molecules. So we drew earlier the electron dot diagram for ammonia, which is NH3. Looked like that. So that's highly electronegative. So you could have a hydrogen bond between ammonia and another ammonia molecule. So the attraction will be right here. And that's a hydrogen bond, this little pink region. It's not really a bond, it's just a positive negative attraction, kind of like the magnets attracting each other are not really stuck to each other, but yet they attract each other. All right, so the reason it's so strong is because if you have hydrogen here and oxygen bonded with it, the water molecule really looks more like this because hydrogen is very small. So the electrons are pulled way toward the oxygen, and the hydrogen is just barely exposed down here, just barely got any electrons, and it's positive. So it makes basically a bare or naked positive charge down here, making it very attracted to anything that's negative that happens to float on by. All right, so hydrogen bonding is really just a dipole-dipole attraction, but the hydrogen bond is the strongest of the dipole-dipole attractions. All right, so that was my attempt to summarize it. I might also mention that the reason we compile so many drops of water on the penny back in that first video is because of the bonds between the molecules, that is the hydrogen bonds.